Okay, so good afternoon, everyone. Firstly, I think somebody asked about the midterm exam, and so I don't mind whenever. Actually, we can have it any time before April 1. So, I mean, I can fit in with your schedules. You probably have, a lot of midterms, and you probably don't want them all to be like in the same week. So, when are most of your midterms? Okay, so 21st. So, let's see. Yeah. So that's like the kind of the week before the very last week that we can do it, because so April 1 is like the dates that I have to submit your grades. So we could actually do it in the week following that one, or we could do it in the week before then. I don't know. What would you prefer? Uh-huh. So basically, the week following would be 20, maybe like 29 of March. Okay. How does that suit? Oh, okay. I mean, the last possible date would be 31. It's pushing it, but can do.
Actually, 29 is fine because my other one is on the 21st week as well. So, yeah, 2 is fine.
Okay. Can we make it the 29th then? Okay, all right, 29. Okay, so that's settled. I'll announce that formally. And so the content of the midterm is usually, what I do is just simply it'll be like a problem-based thing, a bit like the homework questions. So it'll be probably like 1 hour. Just do it in class here. I'll give you a problem sheet and closed book test. Yeah, and basically it will be a lot like the homework questions. So what I always say is that you should really make sure that you are able to do the homework questions comfortably, because that's the kind of questions that you'll see in the exam. So actually, what we haven't really done, I kind of forgot about it, is that we haven't really talked about much of the homework questions. And so in past years, actually, I've often talked about the homework questions during the class, and gone through some of the problems too. So, are you guys going with the homeworks? Sorry, I haven't marked them and given them back to you yet, but are you finding them okay?
Can we have like the homework solutions?
Well, I think if what I normally do, yes, I mean towards the end or something, towards the midterm, I can give you the homework solutions. But I mean, I think we should really talk about it in class. So if there are some particular questions, then we should go through it together in class, and
It's just that I'm not. Oh, you mean like? Oh yeah, we can get our.
yeah. So I mean, we could go through some questions from the homework today as well, if you want.
It's just I don't know whether I'm right or not. That's the.
Sure. Okay. Right. Well, yes. I mean, so that's why I should give you back the yeah, homework. Okay. So if you don't have any particular questions you want to go through today, then I'll try and mark them all by next week, and then give them back, and then we can start discussing the homework. Actually, we've been going through the lectures pretty fast, so we should sort of maybe slow down, take some time to go through some of the problems too.
Just a side word. Do you know like for the final?
Hmm.
Do you like do we have the final like in like at a regular time period like within the like the end of class or in the exam week?
I usually just have it in exam week.
Oh.
Any reason?
Oh no, just asking.
Okay, yeah. I don't have a particularly good reason for that. It's just the exam is just in exam week. I just usually do that. If you have any particular requests for that, then just let me know. But also the final exam will be a bit like the midterm, just an expanded version of the midterm, and then that's also just based on the homework question.
Okay, is it cumulative? Final?
Cumulative meaning?
Like including the everything we learned before the midterm?
Right. Well, yes, but with a bit more emphasis on the second half. Yeah. Because, of course, the stuff you learn in the first half is the basic kind of stuff. So, so there will be stuff which is that you'll need to know from the first half. Yeah. Okay. All right. And, we should also talk about assignments too. So, you guys have you had a look at the assignment problems? Forgot. Well, take a look at the assignments, and I think you're actually supposed to choose a topic and tell me what one you want to talk about later on in the second half. Right? So just you can simply choose one, or you can kind of discuss with me any topic that you prefer. Okay, yeah, probably that this should be also done as kind of early as possible, because you don't want to just sort of try and come up with your whole assignment the night before. Okay.
Yeah, but we are actually going to that the quantum circuit and the gates part. So.
You mean in the lectures we haven't done
because
that
I'm
yet?
like interested in
Sure. Yes.
Yeah.
Yeah. Yes. Right. Yeah. Okay. So, well, it's a balance of we don't want to go through everything so quickly that we've sort of covered the whole course before the full 15 weeks, but of course we want to get there so that you can do something interesting for your assignment too, right? So, okay. All right. So let me just recap what we were talking about last lecture. And so we were talking mainly about observables and how we can turn like measurement probabilities into an actual observable. And eventually we saw that basically if you want to calculate the average of something due to a measurement, then this is the quantity that you calculate. And so the average of some observable R is you calculate it by sandwiching it in between the bra and the Keck versions of the state. And then you, in order to construct your observable, you have some operator like this. And an observable always has some values associated with it. So particular outcomes have particular values. If we're measuring energy or position, the actual value of the energy or the position would be this little r thing here, just a number, scalar. And the state itself, which are the outcomes of the state, are, you create an outer product of those. And we did quite an elaborate calculation on the board last lecture, but basically all that stuff was there just to convince you that of the validity of this formula, that if you want to calculate an average, this is just simply what you do. And it doesn't really matter if the state and the operator are kind of written in terms of different bases. You just put it into the formula and it will calculate the average for you. And so the way that I convinced you that this was true was by just firstly evaluating this formula. So this is just calculating whatever that quantity is, but you can also calculate the same thing from first principles, if you like, which is that observable should always be sum over some probabilities, or an average over probabilities. So it should be like this. So these are the probabilities of the state written in this n basis. And then we showed that these two expressions just give the same thing. So basically kind of a proof to show you that this formula really does work. Okay, and then we looked at a particular example of observable. So even though I said observables are some kind of physical quantity like energy or position or something. Actually, these observables are still a little bit abstract because it's not really like it's not like position or energy. These values don't really have any units actually, right? So it's just plus or minus one. But basically, these things are kind of sort of generic quantities that you can look at to kind of try to understand what the type of state of a qubit is. So these are just relevant for qubits. So basically, so there's three of these so-called Pauli operators, x, y, and z. And basically in all of them, the value is either plus or minus one. And the only thing that's different are these bases. So the 0 and 1 is a particular basis, but plus minus is another kind of basis, and then this plus y minus y is another basis set. So basically, why is it values of plus or minus one? You can just think of it as a kind of a meter that is just measuring, okay, so is it more on the one state or is it more on the other state? And then basically the positive or negative things just sort of tell you which way it's skewed, right? That's just like a variable that sort of measures how much it is one state or the other state. So if these are like, it's very much, say this probability is much more biased towards 0, then this thing would be like a positive value, close to 1 or something. If it's very much skewed this way, then it would be a negative number. And we can write down these things in terms of these in the matrix representation, and basically they're all 2 by 2 matrices, and they are of this form. Z is a diagonal operator. The X is something with off diagonals, and Y is off diagonal, and it has some complex values. And so I think what we did as an exercise in the class is to calculate the expectation values of X, Y, and Z. So got each of you to do it, and then what we saw was that these things look just like the formula for this one, and this one. Looks just like the formula for spherical coordinates of on a unit sphere. So this gives us a very nice interpretation for visualizing all the possible states on a qubit. So I said to you before that this state here gives basically all the possible qubit states, and there's just two parameters there. And so we can basically visualize the state by some position on the sphere, because this kind of gives you a coordinate on the sphere, and basically each point gives a unique state, and it's a different point, a different state. This is why we use this particular parameterization, and this is sort of why we call these things x, y, and z, because actually those are the coordinates. In Cartesian coordinates, spherical coordinates. So spherical, these angles become like these expectation values. Okay, so that's just a bit of revision. We actually just got to the end there. Anything you want to ask about that stuff there? Well, I guess it helps you to visualize it. So if you say, okay, here's my quantum state. It's always helpful to have a kind of a map of where you are, right? Like saying, what's the point of maps? I mean, well, maps are very useful actually, right? So you know where you are. And you know how to get to various places and stuff like that. So in the same way, this block sphere is a very nice map for the qubit states. And I mean, it's, well, maybe it's obvious from the fact that these are trigonometric functions already, right? But it also does show you that somehow the way that these states are it's kind of, it has this sort of spherical topology, right? So perhaps you might have not noticed that if you just wrote it as just a bunch of complex coefficients, right? So if you just said alpha, beta, then you might have not noticed that actually maybe this state and that state are actually very close together, even though, the parameters might look quite different. Imagine if it's like, a state with phi with pi minus epsilon or pi plus epsilon. They might look very different, but actually the states are all just about the same. So it kind of gives you a sort of a map of all the states, and it also tells you sort of how to get from one state to another. So I don't know. I think that's the main reason why it's kind of a useful concept. I think I mentioned this before, but it's not, I think people have tried, but generally there's not really a good way to visualize high-dimensional systems. So qubit is actually the simplest possible quantum system, just two levels. And it's simple enough that we can do this visualization. But for like a high-dimensional system, like three dimensions or four or something, basically there's too many variables, and it's just like you can't really visualize it very well. Okay, all right, so maybe there's no other questions. We'll leave it at that. And maybe we can talk about something a bit lighter or heavier or bit different this time, which is interpretations of quantum mechanics. So this is where sort of this topic kind of touches a little bit on philosophy a bit. And that's interesting because this is supposed to be a hard science, and hard scientists tend to sort of stay a bit away from philosophy, even though actually a lot of people have interest in philosophy, because after all, both philosophy and physics, we're both trying to get to the bottom of what is the most fundamental kind of truths in the world. And well, the approach is quite different. Physicists take quite a scientific, mathematical type of approach, and philosophers take a rather different approach. It's a bit more of a humanities kind of flavor to it, but in a way the objectives are a bit similar. And it's interesting that quantum mechanics, because of the nature of the theory, and I mean, after all, it is a way to understand reality. But then the reality is so weird that it starts to bring up some kind of philosophical types of questions where start to wonder, what is reality? So this slide set is basically it's not really technical at all. There's no real equations, but what I'm going to show you are basically various different ways that people have tried to understand quantum mechanics and tried to sort of make sense of it, really. So so basically there's a couple of sort of puzzling areas in quantum mechanics, and we've already encountered some of them. The main two sort of puzzling areas in quantum mechanics are this kind of nature of the measurement, right? And the other one actually is entanglement, which we haven't talked about yet. But anyway, the measurements is already enough to sort of start to talk about some of these questions, right? So we saw that measurements, the way that we've been kind of discussing it at this moment, you have some wave function, and it's originally in this state here, and some kind of measurement occurs, and then it becomes this state or that state. Probabilities are these things squared, and this is a completely random process, right? Now, this was just a more, kind of the simplest possible example. We're not going to really do this in this course, but this also applies to anything with more degrees of freedom. It even applies to continuous systems. So this is a kind of a discrete example. It's just two states, but you can also have like a continuous system, and in that case, you might have like a continuous wave function like this. And basically how you visualize a collapse or measurement process is that, before you had this wave function, and then after the measurement, somehow this wave function collapses to some particular value, right? Just like here. So you had the wave function before, but afterwards, kind of no more wave function. Could say that's the wave function, new wave function now, but at least that original wave function is just gone, right? So, it sort of makes you wonder why is measurement such a sort of a special process in quantum mechanics, and why can't we just go and simply sort of if this thing is supposed to be there, why can't we just go and measure this thing? Why is it that it sort of just disappears when we look at it? Right? And so this starts to sort of raise questions of, well, is this wave function thing that we've been dealing with. Apparently, it can predict all kinds of things. It can calculate wonderful things about atoms and predict like energy levels, and then it all theory great, right? But at the end of the day, you sort of wonder, well, what is this thing anyway? Like, you look at it, it disappears, and is it even real? Like, is it really something that's actually existing? Or is it like something that's actually that you've, it's like a convenient mathematical invention that gives us the answer, but it's not really something real, right? It's just sort of a kind of a construct to help our, poor human brains, because, we don't really understand the thing, but we invent some funny mathematics, such as to make us get the right answer, right? So basically, this kind of discussion is really centered around saying, really, what is this wave function after all, and what's with this whole weird measurement process? So basically, there are various types of interpretations that people have developed through the ages to try and make sense of this whole process and the existence of wave function. Okay, so these are just some kind of points of view, and this is not supposed to be like a comprehensive list. This is somehow just various different points of view that people, I feel, tend to have. I think there are even some other ones, maybe Bohmian mechanics, things like this. I don't fully really understand, so I'm not really going to talk about them, but these ones are some of the sort of the major ones. Okay, so the first one is this so-called realist interpretation of the wave function. Okay, and this one is actually sort of an outdated theory now, but I'll tell it to you anyway. So basically the way to understand this is a similar way that we understand probability distributions. Right? So when you say, you have a probability distribution, that could mean, that can actually arise from a few different kind of situations, right? So you could have a situation where, for example, something is random because maybe it's like too complicated to understand, or like throwing a die. In principle, like if you throw a die at a casino, right? Like if you calculated the full trajectory of the die and then how it bounced and looked at all the materials and all this kind of stuff, in principle you could predict what number is going to come out in the die, right? But we sort of don't, or we generally don't, because it would just be such a complicated task that we just say, okay, well, I know in principle we can, but it's just too hard, don't bother. And so, one way that such randomness can actually occur is basically kind of due to the lack of knowledge of our system. And the example that I kind of like to do, which is given on the left here. So, do you guys remember that airline that went missing? Malaysian Airlines. So it flew out from Malaysia and then it went somewhere and just kind of disappeared, right? Now, that airplane is presumably still somewhere. Was that ever discovered? You guys? Some pieces, yeah. I think basically, but still to this day, it's not really completely known what happened to it, which is amazing in the 21st century with all the technology and all this stuff. It's amazing that you can just like lose a whole plane. But what you do know is that, well, this is where it was flying, and this is where this is the 4-hour flight range. So of course you know the speed of the plane. So you know that the plane has to be somewhere here, right? Now the plane is actually somewhere, right? But you just don't know where it is. Right? It's not that like the things just disappeared or something like that. It's literally somewhere, right? But you just simply don't know. So a probability, you could describe this as with some kind of probability distribution, right? You could say, well, the probability of it being sort of around here is maybe rather high, and maybe right on the edges, the probability would sort of go to zero, because basically that, well, the plane is only so much fuel and it can't fly faster than this, and so forth. So basically the probability would sort of be higher and lower in certain areas, right? So this was sort of one kind of interpretation. So in the early days, so people said that, well, maybe wave functions are sort of like that, right? Like maybe it's like when you measure it, right, you get 0 or 1 or something. And you get 0 or 1 not because it's like something's happening between this step and this step, but basically it was always in 0. You just didn't know that it was in 0, right? So this would be a kind of a realist interpretation, so that you don't. It's just reflecting the lack of knowledge of the system, and basically the wave function is just some mechanism in order to describe the degrees of freedom, or the potentiality of the thing being in this various different situations, and then eventually when you measure it, you find out where it is, and then, so that's what's going on when you do that. So Einstein was sort of in favor, I guess, of this kind of theory. Einstein famously said that God does not play dice. So he didn't like the fact that fundamentally at the the most foundations of physics is this kind of random behavior, and so he basically was saying that, well, nature shouldn't be like this, that there's some inherent randomness to it. There should be some fundamental thing that you can actually pinpoint. A more modern way to describe this situation is that there is you call this a hidden variable theory, basically. And it's a hidden variable because basically there is some variable there, like in this case the location of the plane, I suppose, that you don't know about, but actually it's really there. So if you were to write down the probability function, then like this variable would actually be in there. Okay, so that's the realist perspective. In fact, what I'll show you in a few slides. Well, I won't really show you, but I'll just sort of tell you. But actually, you can actually disprove this theory, which is actually very interesting in itself. So you can actually create a theory and perform an experiment to actually show that this just cannot be true. And so in a way, well, this actually proved Einstein wrong. Einstein is almost right at everything, but in this example, Einstein is considered to have sort of got it wrong. Now, the most common perspective that physicists take, and this is probably like over 90% of physicists, is a little bit more like how I explained it in the first place. So, if you're saying I'm sort of guilty of sort of kind of already telling you or teaching you in a way such as it's already colored in an interpretation, then I suppose probably the way that I told you that is a little bit more along these lines. And basically the point of view that this one takes is that the wave function, the state before the measurement and after the measurement really does change, right? So before the measurement, it really is in this wave function. And after the measurement, it changes into a new wave function. So, that's the way that I described it to you. But that's actually a sort of a so-called Copenhagen interpretation. Why is it called Copenhagen? Copenhagen is a city in Denmark, right? I think Niels Bohr was there, and Niels Bohr was one of the first guys, to think of these types of, he contributed to quantum mechanics, but he's also very famous for debating with Einstein what the real, nature of quantum mechanics was, and Niels Bohr was sort of on this side of the camp. And basically, in the Copenhagen interpretation, the measurement is a kind of destructive process that actually changes the state. So the state actually changes with the measurement. So, the way that I like to think of it is that, these quantum systems are like really tiny, very microscopic, they're at the atomic level or they're a photon or something like this, right? And then here we are, these kind of giants that are trying to measure this thing, right? And like a giant who is trying to measure this very tiny, delicate thing, as soon as you try to look at it or measure it, you just crush it in your fingers, right? So basically, it's like this kid who's just trying to measure it, and even it doesn't matter how delicately you try to measure it, you just smash it and just destroy it. So it's actually kind of a reasonable analogy, but actually, eventually, what people showed is actually there's not really any good way to really measure it. So it's not just because we're giants and we're sort of idiots and trying to measure this small thing. Actually, even if you really did it very sensitively, you still can't measure it perfectly. But then this sort of raises the question. Okay, fine. This state changes before and after. You can accept that. But then what does this really mean in the end? And so the Copenhagen interpretation says that particles basically do not have definite properties prior to being measured. Quantum mechanics can only predict the probabilities. Right? So basically, this Copenhagen people would say that this is a kind of an indeterminate state. It's not really 0. It's not really 1. It's just in this. It's indeterminate in the sense that it hasn't been determined yet. Measuring actually changes it into this determined state of being definitely 0 or definitely 1. Okay. So despite Copenhagen being the most sort of popular position to take, so there's still many kinds of conceptual problems that make people a bit uncomfortable. So, for example, when you do a measurement, apparently it just sort of suddenly changes from this one to this one. Right? So, that seems a little bit strange. It's like discontinuous in time, like just suddenly jumps. Why does it have to jump? Actually, this one can be counted. So you can actually do a measurement so that you sort of do it in small steps. It's called weak measurements. So actually, this is maybe not so much of a problem anymore, but in the early days, I think people didn't really understand it, but I think modern days, it doesn't have to be discontinuous. So maybe I would remove that one from the list. But certainly, the second one, probability cannot be eliminated. Yeah, so yeah, you sort of always end up with these probabilities. You can't really get around probabilities. So, you know, there's no way of, for example, turning this into that deterministically. Sorry, I mean with a measurement, that is. So if you're doing a measurement, you either get one of these randomly, and that's just part of quantum mechanics. Another objection that people might have is, you know, this measurement kind of sounds like somehow people have something to do with this, right? And you know, in the Schrodinger's cat experiment or thought experiment, some people sort of, I think, mistakenly interpreted it as, you know, maybe it's like consciousness doing something. You know, like maybe it's because you were there and you're looking at it that changes something. This is again not really true, but kind of has the kind of looks like that, you know, this measurement requires some kind of observer to it for this kind of collapse to occur. Actually, it's what people now understand is that actually measurement is very much like a process of decoherence, which I'll get to in a minute. So yeah, you actually don't really need like something that's alive or anything like that. A machine can do it just fine, or it might just happen on its own just fine too. Yeah, people also in the early days had trouble. So how do you make a measuring device, or you know, what exactly is this measuring device? We did things like with measurement operators and things, but you know, what the hell is that actually? How do you even derive that thing? And then maybe the final problem with this is that, well, you know, so here's our quantum system, and apparently this measurement is classical, right? But so somehow this quantum thing is linked eventually to this classical thing, and you know, how does all that work? So so classical physics still comes into it. So so I'm not saying that all these problems are still relevant, but these are sort of various questions that Copenhagen interpretation kind of raises. Okay. Now this one is not so popular as such, but I did see it in the textbook that's in the recommended text in Griffiths, so I'll include it anyway. Another interpretation is to say that, well, you know, the question is flawed because essentially what we're doing is to say, you know, so but what happened before the measurement, right? But then if we're asking some question like what happened before the measurement, that sort of saying something like, you know, well, you know, it's an unanswerable question because science is based on measurements, and you're asking what happened before the measurement, but then, you know, how can you do science on something that you didn't measure? So you sort of say that, well, that's you know, the question is meaningless, but well, I don't think it's meaningless. I think it's a totally valid question because, I mean, we've got a whole theory to describe this whole thing, right? So we better understand what the hell we're dealing with. Yeah. This one is quite a famous interpretation. Have you guys heard of the many worlds theory?
It's these
Mm.
are true.
Yes, exactly, yeah. So basically, in the many worlds theory, which sounds like a really crazy theory, what happens is to say that, okay, well, actually, what happens is not that this thing collapses, right? But actually, every time you do a measurement, you branch into a parallel universe where you only see that outcome, right? So if you get 0 in this case, what that means is that you've branched off into this universe where that's happened, right? But then there's another universe where the other outcome happened, and you don't see that other outcome because it's in a parallel universe. It's gone. And basically every time you do a measurement, you keep on branching into these number of universes. Now this sounds like a really crazy theory, but interestingly there are some people that actually do support this theory, and quite famous people that kind of support this theory. So David Deutsch is one famous person that supports this kind of theory, and David Deutsch is actually one of the guys that really started off this field of quantum computing. So it's sort of considered one of the really early pioneers of quantum computing. And but he's a quite an eccentric character, which I think he's at Oxford or Cambridge. I can't remember which one. And so he's still there apparently, but I think really leaves the house and things like this. But yeah, no, other people, I've heard people believe this kind of theory, and I don't know this. So just my kind of anecdotal kind of observation is that it tends to be the people that are like real kind of mathematicians that tend to believe this kind of interpretation. So I think what tends to happen, well, this is just my imagination of what I think happens, is that when people really believe the mathematics on the page, right, and they really take it kind of literally, then I think those types of people can sort of believe this type of interpretation. And as with all these except for the first one, these are all interpretations, and so it's very difficult to really sort of kind of say one's wrong or right, because it's just like equations on a page, and you're basically asking what really happens, and that's it's a kind of a subjective thing in a way. So yes, many worlds theory. And yes, I mentioned decoherence, and this is particularly important in the context of quantum computing because basically decoherence is, so people originally wanted to sort of understand, so you have a quantum system, but apparently we live in a mostly classical world. How does something quantum become a classical thing? Right? And the theory that some people came up with, Zurich is a famous name, and that kind of invented this theory, is that essentially decoherence is something that very commonly happens, which is that if you have a quantum system, what can happen is that it can easily interact with stuff around it, and then that can essentially introduce noise into the system. Actually, a little bit more precisely, it actually introduces, becomes sort of entangled with the things which are surrounding it, and that effectively creates noise. And the way measurements are understood in this context is that basically the system becomes affected by the things that are surrounding it, and that basically causes this measurement. And so in this decoherence theory, the way that people understand it is that decoherence actually is really the same thing as measurement. And measurement is just a type of decoherence that humans just inflict on the quantum system in order to try and understand something about it. And decoherence is just the same thing. It's just that, it just happens without you really particularly trying. And basically, both of these things can sort of explain how this type of collapse occurs. The only real problem with this is that it can't really essentially, when you do this kind of analysis, all you end up with is that you have the system, and then it's entangled with another system. So you have your qubit, and then the noise, the things around it gets entangled with it. But then, how does this random thing happen? It doesn't really explain that actually. It just explains that, well, you can understand. You can kind of get these probabilities, but just this random thing, it doesn't really explain where that actually comes from. So it's only kind of a partial explanation, and it doesn't really explain why we only see like one outcome when we perform a measurement. So just going back to the first interpretation, the one with the airline going missing. So we might do this a bit later in the maybe second half of the course, but there's actually a way of showing that, well, for a particular case, that it's impossible to have a hidden variable. It's basically impossible to have a situation where you have this kind of randomness because there's something you don't know, and basically the way that this was proven was using some kind of entanglement detection. And so in an entangled state, if you perform a measurement on two sides, what you'll find is that they're correlated. And quantum correlations can actually be much stronger than classical correlations. And so by taking advantage of this point, you can actually show that you can actually get correlations which are impossible to make with just like a classical probability distribution. So basically what this John Bell did was to imagine a particular situation and say, okay, well, let's write down the most general probability distribution with as many variables as you like, right? So probability distribution, a huge number of variables. And let's say that, we're looking at this situation where we're looking at particular random events and there's some correlation between them. And then let's try and derive, how much correlation can you possibly get in this situation, just with the most general probability distribution you can possibly write. And you can work out that there is some bound, some maximum amount of correlation that you can get even with the most general probability distribution. And then basically what you do is then you do the quantum version of this and then show that it exceeds this bound. It's like impossible to get that level of correlation with any probability distribution. And so basically this kind of disproves, at least for this scenario, that first case, that this wave function is just something that describes the lack of knowledge of our system, because if you can't write it with a probability distribution, then basically you can't possibly have such like a hidden variable in anyway, well, probably doesn't really click until you really see the equations and do the calculation, which we will do a bit later. But basically, this was just to sort of show you that there's different types of interpretations, and well, measurement problem is actually still a kind of a problem that exists in quantum mechanics now. So there's not really a very satisfactory way of understanding why this measurement process is random. So it's a kind of an open question, but maybe by now, I think 100 years after quantum mechanics has been developed, I'm not sure if many people are really working to get a way to try to understand it more. So, if it hasn't been solved in 100 years, then maybe it will never be solved. And it's just that this is just the way nature is, and all we can do is just to describe it mathematically, and then maybe our job is done. Maybe there's nothing more to interpret. It's sort of a Copenhagen way of thinking. Any questions? Any debates you want to have?
What is this experiment actually doing at
Right. So we will do it later, actually. But what is it actually doing? So it's got a source, and this is a type of, basically a type of crystal. And if you type of crystal where if you some crystal, right? And if you shoot a photon into it, it will split kind of the photon into two, each with half the energy. So if this was some frequency HF, then these ones would have a half HF each. So energy is conserved. Now, why do we want to split a photon into two? Basically because what people found is that actually the photon becomes entangled with each other after it comes out. So basically this thing is just a way of making some entangled photon pair. And then you just maybe put some mirrors here, and then, and this photon will go over here, and this photon will go over here. These things are still entangled, and you can perform some measurements on them. And basically, how they entangled, so photon has like two polarizations. So the photon can be like, say, vertically polarized or horizontally polarized. And when you have an entangled system, essentially these become kind of correlated, so that say you measured horizontal polarization here, then you'll get horizontal over here. Say you measured vertical here, then you get vertical here. That's okay, but what's having something correlated with each other is not necessarily only a quantum thing. You can have correlated things, because if you just put two balls of the same color and then they just shoot them at the opposite end, in different directions, you can get something like this. But what's interesting about the quantum case is that you can, if you measure plus here, and we've already done measurements in other bases, right? So you can measure plus here, and plus meaning in this case h plus b. Then you also get plus here, and if you measure minus, you also get minus here, and actually even any other angle. So this is just 4 examples, but you can change this basis to any angle, and you'll always get the same thing. And then so this is what you don't get classically. So you can do h and b just getting the same thing, but getting plus and minus to be the same thing too is more of a quantum thing. And basically what this guy did was to work out correlation between various measurement outcomes here and different settings of the measurements that you do here. And because of this kind of super correlation that you can get between these quantum states, basically it sort of exceeds the maximum possible correlation that you can possibly get with a classical probability distribution. So yeah, that's basically what that setup is doing there. It's like basically it's a photon source. This is like a polarizer to measure the polarization of these things. And then this is just something to figure out whether you've got the same outcome or not. Any other questions? Yeah, 10 minutes left. I don't think I really want to start a new topic. So if there's no questions, and we have an early mark today. All right, okay, we'll leave it there.